Go for it.
Good questions. Yeah, thanks.
And sorry, 1 second. Are you wearing the microphone? Are you still wearing the microphone? Where's the microphone? Okay.
Oh, sorry. My microphone.
Excuse me.
So like that.
Thank you. Yeah, no problem. There you go. Let me take that. That's the mic. Just click on
Yeah, just yeah. Okay. Hello. Can everybody hear? Yeah. Okay. Yeah. So so I will be presenting OVerSeeC, an open vocabulary CostMap generation pipeline for satellite imagery and natural language. So let's go into our problem. So we have our robots and we want to go from a start location to a end goal location, and we have satellite images. So for that, we would need some global paths. So here are two global paths which were made by a human. So what makes these global paths viable? Seeing into the semantics, these global paths are mostly through trails, roads, and grass, and they try to avoid trees, water, lakes, and warehouse and settlements. So as a human, we had a preference that we wanted to go through trails, roads, sometimes through grass, and avoid the others. So to heed to these preferences, we need to have a very good understanding about, like implicit or explicit understanding about the different semantic classes. Seeing into the semantic classes, there are some semantic classes which are common across all the environments, and there are some which are very specific to the environment and mission. So we have 4 challenges. The first challenge is there are some common classes, but these differ visually from environment to environment. So a tree in Austin will be very different from a tree up north or in a snow-clad mountain or a tropical area. And this requires additional training and additional data collection and retraining. Even if we solve this problem, we have the problem of classes which are very novel. Such as, suppose we want to avoid an electric tower or go through the bridge or go underneath the solar panels or avoid the railway track. So do we just collect more data for this and do a complete retraining for that? And the last 2 challenges are, some classes can have different affordances. So some bushes can be traversable. So a bush in Texas can be traversable, but a bush from Pennsylvania maybe not traversable. Or there are some mission specific factors, such as you want to go through the sports, you don't want to go through the sports field, but you can go through the grass, and sports field is a type of grass. And so you need to have a very good understanding about that. Or maybe you want to go through the center of the road or through the side of the road. So to heed to these preferences, you need to have a lot of changing of the CostMap. So seeing into the challenges, here is our current practice that we generally follow. We identify relevant factors, we collect environment specific training data, and then we retrain or fine tune our models that we have, do some small scale tests, and once we are happy with this one, these steps from 1 to 4, we start deploying. And this is very tedious and time consuming. So is there a better way? The dream CostMap generator would be, we have a satellite image, we pass some relevant factors, and boom, we get a CostMap out of it. This should be a fast process, and we should not do any amount of retraining on it. So OVerSeeC is an attempt to that. We have satellite images, we have some natural language prompt from the operator, and OVerSeeC tries to get the CostMap out of it. And so here is a video of what we want. So we first zoom in to the area of interest, crop it, and then give some CostMap about some preference that we want to go over trails but avoid the river. We get all the classes from that. Then we get the masks for each class. And then we have some kind of CostMap that we generate. Once we have the CostMap, we are happy with it, we generate the CostMap. Once we have the CostMap, we plan over it, add a start and an end goal, and use some global planner like A star. Maybe we are not happy with it. Let me pause it. Yeah, maybe we are not happy with it. The path that we got is going through the grass and we just want to go over the trails. So as an operator, we would add some more prompts like try to stay on the grass only when necessary. And we see that the grass has been given like a higher cost, like 700. And so once we have the cost map, we generate the cost map, and then we plan, like give the start and an end goal, and we have this, this path, which is not going over the grass and going over the trails. So this is the dream model that we want. And so how do we do it? So the first question is, can we use a foundation model to solve it? And I would be very interested in the panel discussion that will be happening today about how being foundation models in off-road robotics, whether it is a hype or reality. So we asked a monolithic model, an LLM, to do that. The first thing that it does is do color-based thresholding, and the same semantic class can be visually different as we have seen. And for one type of grass, it gives high costs. For the other, it gives low cost. Or if you use the image generation tool, it gets the concepts right, but it's not spatially consistent. And so our answer to this question is no, but can we still use foundation models because they are really good at specific tasks? And our answer is yes. So we can decompose the problems into subtasks and then assign each task to like different foundation models. Here is our subtasks. The first is understanding what are the terrains and entities of relevance. That can be done by an LLM. The second one is, given a satellite image, given the classes, we can generate per class, per pixel masks, which can be done by a language-grounded foundation model. The last bit is, once we have the masks, we want to compose them together. And so an LLM can generate a function that can combine these masks together. And lastly, we have a system which combines all of these things together and gives a cost map. And so we name these as the class identifier, the open vocabulary mask generator, the cost map compositor, and lastly the cost map generator. Let's see into the first one, the class identifier. So we have an LLM, we add a natural language prompt, and this gives us the classes. The blue classes are the classes which are common across different environments and settings. The green one, which is the river, is an open ontology class. Once we have these classes, we have the satellite imagery, we pass it through the open vocabulary mask generator, which gives us per class masks. So we use a model called ClipSeg, which takes in the satellite images and classes and gives us the semantic segmentation masks. But the problem with this is it's coarse and it's very blurry. So to solve this problem, we again use a foundation model. So we have these semantic masks from ClipSeg. We have a point exemplar which takes points from these individual masks and this then passes it through SAM. And SAM gives us like the fine masks. So this is a comparison of the coarse masks from ClipSeg and fine masks from SAM. And this is the entire overview of the open vocabulary mask generation pipeline. Once we have that, lastly, we want our, we have an LLM, we pass a natural language prompt, and that gives us a Python function that heeds to the user's preference. So once we have everything, we have the masks, we have the Python function or the CostMap function, we combine them together to get the CostMap. So this is an entire overview of OVerSeeC. So we have the satellite image, we have the cost map, so we can take a global planner and plan over the entire map. So now that we know what OVerSeeC does, let's see into how it performs. So let's go into evaluations and results. So for evaluation, just to make it clear, we are only passing satellite images and a natural language prompt to any cost map generator, which gives us a cost map. And then to evaluate how good these cost maps are, we are using an A-star global planner so that we can quantitatively and qualitatively evaluate the paths that are generated. So for baselines, the problem is there is no such model that can do the entire thing. So we resorted to replacing the clip-seg with fixed ontology semantic segmentation models like segformer or a unit with a Dino backbone. And we trained it on OpenStreetMap's data. This is the first metric. We did some human evaluations in which we had certain maps, we gave starts and end goals, and we have some natural language prompts. The human evaluators drew the path over the map. The blue ones are, the green ones are from human evaluator. The red one is OVerSeeC seg, which means OVerSeeC with segformer, which is our baseline. And the blue one is our method called OVerSeeC. And so we calculate the Hausdorff distance between the paths that were drawn by the human with the paths that were drawn by OVerSeeC or the baseline methods. And the lower the distance, the better. And so we see that OVerSeeC performs way better than the baselines. And we did some sensitivity analysis in which we make a confusion matrix of OVerSeeC versus human, in which we had the same start and end goals, but we changed the prompts for it. And the idea is the diagonal elements should have lower Hausdorff distance than the elements which are off diagonal. And we see that. And this proves that the LLM is actually working and makes CostMaps which heed to the human preferences. This is the second metric, which is more quantitative. So we have this metric called rank regret path integral. So we can calculate the rank. So the rank is basically given in a natural language preference. We calculate, like we assign ranks to roads, grass, and other classes. Once we have this rank, for each pixel, we have a particular class. Each class has the rank for it. So each pixel has the rank for it. And then we subtract with the best rank, that is 1, and we get the rank regret. And then given the path from the A-star planner, we calculate the RRPI metric by using path integral. And the idea is lower the path integral, the better. So here is how we do it. So we have a map. The prompt is to avoid the baseball field. We spawn 50 random start and end goals, and from that, the A-star planner plans over the CostMap. These are like 3 representative examples of it. Once we have that, we calculate the RRPI metric, plot it against the path length. And so these are some quantitative analysis. So there are 2 cases. One is the in distribution case, the other is the out of distribution case. For in distribution case, we see that our method performs very competitively with the baseline methods and outperforms in one of the cases. And for the out of distribution case, it performs really well and outperforms like the baselines. So concluding, OVerSeeC is a zero-shot test time adaptable pipeline. It adheres to human preference. It is interpretable and it's neuro-symbolic, and it's modular and upgradable. If something new comes up which is better than clip-seg or SAM, we can just change that, but keeping the pipeline the same. And so the future works is like there are certain limitations. First of all, we need a very good tight integration between the perception modules such as the semantic segmentation and the SAM module. The second is we need more nuanced handling of how we handle the semantic hierarchies. Lastly, our model is not robust to artifacts like shadows and occlusions, and so we need a module for that. And so, thank you. That was my work. Yeah.
Thank you very much for that talk. So we've got, so the next speaker, again, we'll set up and we've got about 2 minutes for questions. So the next presentation is online adaptation of terrain-aware dynamics for planning in unstructured environments. So any questions from the audience? That poor microphone today is having a rough day. Any questions from the audience?
Generating the what? I mean,
the Python code. Like, is it really required that we have like Python code to do this in this scenario, or why did you choose this?
No, I didn't get your word.
So you have a Python code that
Oh, Python code. Yeah. So, I mean, you need to, so there are these complex preferences, if I can go over the details. So, such as you want to avoid the baseball field, but you don't want to avoid the grass, and baseball field is a type of grass. So to know those complex understandings, you don't want to like change the CostMap for each case, and we don't want that. So the LLM actually helps you to give that Python code, and Python code is basically a medium to like combine all the masks together and give you the CostMap. So yeah.
Great, thank you very much.
Thank you.
One more round of applause.